Hello everyone. So today we are going to talk about probabilistic learning and sampling methods. So this lecture is a quick recap from machine learning course, but also with some new perspective, new algorithms, mainly sampling algorithms. And this is very important, so please pay attention to these methods because they will lie down foundations for evolutionary algorithms for our next meetings. All right, so let's start. So what is probabilistic learning? Let's say that we have a random variable and this is tossing a coin, right? So this is a random variable C. It can take two possible values, 0 or 1, okay? And let's denote by x probability of observing a head. Okay, so C equals 1. And since probability must sum to 1, so the probability of C equal 0, so it is just 1 minus x. And the probability distribution for a binary random variable, it's called Bernoulli distribution, and we can express it as using one single formula. And so probability of C, whether this is 1 or 0, is x to the power of C times 1 minus x to the power of 1 minus C. Of course, if now C equals 0, so this will be x to the power of 0, so it will be 1, and 1 minus x to the power of 1 minus 0, it's just 1 minus x, so we see that we recover the original probability. So this is a nice, neat way of writing it down. So this is exactly what I said. So if we set C to 0, so we will have exactly 1 minus x, and if we set C to 1, we'll get x. So it's fine. So we can, in this nice manner, encode this probability. And we assume that we have our data, so we have these tossed coins, and we assume that these are IID. What does it mean? It means that every single event that we toss the coin is independent, and all of them. So this is one single the same coin. So this follows exactly the same probability distribution with the same parameter x. Okay. And for example, we can start tossing a coin, and let's say that we have tail, tail, head, head, tail, head, head, for instance. And how we can model the probability of data. So this is the concept, the term called likelihood function, the likelihood function, okay? And what is the likelihood function? The likelihood function is the, let's say, probability of all events we observed, all observations. And since we assume that they are independent, so we can write it as a product of a multiplication of probabilities of all individual events, okay, observations. So this is PC1 times PC2 times PC3 up to PCN, okay? So this formula is only true if we assume that our data are IID. Okay, so how we can turn it into an optimization problem? What is going on here? What we are going to look for? And of course, we are looking for the probability, the parameter x, and we want to find such x that minimizes the negative log likelihood. Okay, so as we see, we have a minimization problem with constraint x because it must be between 0 and 1. Some remarks, right? So why negative? Well, because this is what we discussed last time. If we use some optimization packages, the nomenclature, the convention is that we do minimization instead of maximization. So we just change from max to min by considering negative function. And now you can also ask, why do we use logarithm? And the reason is very simple. So first, logarithm of a product is a sum of logarithms. Okay, so this is very useful because if we if we consider, for instance, calculating gradients, so then gradient of a sum is just sum of gradients. So we use this simple fact to just also simplify our calculations. However, also importantly is that important fact is that the optimum is the same whether we take logarithm of product or sum of logarithms. Okay, so logarithm function doesn't change optimum at all. So this is very good news because we get some extra simplifications, but still we can calculate exactly the same solution. And so let's try to solve this using gradients. Okay, so let's do it step by step. So first we take our log likelihood function. So we turn it into a log of product. Then by applying this rule that log of product equals sum of logs, so we change it to sum of logarithms of p of c n. So now if we forget for a second about the sum, so we have logarithm for a single event, single coin or tossed coin. Then we plug in the term for Bernoulli, definition of Bernoulli distribution. So we have logarithm of x to the power of cn times 1 minus x 1 to the power of 1 minus cn. Since this is again a product, so we have logarithm of a product, so we can change it again to simplified form. So now we use two properties of logarithm function. So first, log of exponential function, it could be simplified so the exponent goes in front of the log. And then if we have again product, logarithm of a product, so then it's sum of logarithms. And now we have our log likelihood function in this form, that it's sum of and some sum inside. Okay, so now we see that, and we are looking for x. Okay, so remember. So how we can find an optimum? So the simplest thing is to calculate derivative and set it to 0. This is the analytical way of calculating it. Okay, to finding the optimum solution. The optimal solution. So how we can proceed? So we just take derivative with respect to x of our log likelihood function, right? And we set it to 0. What we can do? So we just go, as I said before, so derivative of a sum is sum of derivatives. We can generalize it to gradients. So now if we calculate derivative and we take advantage of the property that derivative of log of x is 1 over x. This is true for non-negative x's, and this is the case because x is between 0 and 1. So we have sum of cn divided by x minus 1 minus cn divided by y minus x. If we reorganize everything, so we multiply by both sides by x times 1 minus x, we are getting closer to our solution. So now if we reorganize everything again, so we just multiply everything, so we can end up with the solution that is x equals 1 divided by n sum of cn's. What is this? So ladies and gentlemen, this is just an average. So the idea is that the best solution, the best what we can do for the objective function that is the negative log likelihood is just the average. Okay. And for example, if we take our observations from the previous slide, we see that this is almost 50-50. So it's 50% of having head and 50% of having tail. So it seems that this is just a standard coin and there is no big deal. And so now you can ask, all right, so why do we bother? Why do we define everything like this, in this way? Why we know, it's intuitively, we know that actually taking average is a good solution. Well, so we are doing it because further, when we'll talk about neural networks, and in general, if we look at machine learning, So machine learning relies on the log likelihood approach a lot. So this is one of the biggest, I would say, direction, or this is some of the methodology that it's used in so many places with extremely many applications. Okay, so this simple example shows how to formulate the whole problem. Okay, so now please think about it from this more abstract way. So when I approach the problem, right? So I need to determine what is the probability of interest. So some random variable y, right? So I have a probability of random variable y for given some x, and x are some parameters that we are looking for. Then we need to think of what is the log likelihood function, right? So is it IID or this is not an IID? In most cases, we deal with IID examples. So they are identically distributed. All of them follow the distribution of P of y given x, but they are independent. So there is no dependency between two observations. Then we need to check constraints, right? So for instance, maybe x is some physical parameter. Maybe it cannot be larger than something, or maybe I know that some values cannot be larger or smaller than some, my prior knowledge about this problem. And then we need to find the best solution by minimizing negative log of p of t given x, so the negative log likelihood. So this is I would say, the general approach. So this is how to approach the problem, how to formulate the problem. So you see that there is this modeling part when we need to determine the probability distribution of P of y given x, and then we need to define constraints. We need to define objective function. This is the log likelihood function. Then we need to check the constraints. Okay, so this is the scheme that repeats everywhere. Okay, so please remember this very simple example of tossing a coin, because it will reappear almost everywhere in machine learning and also computational or artificial intelligence. So we can take, like, for instance, Bernoulli distribution, Gaussian. It could be conditional, like in neural networks, so that for given image we want to predict some label and so on. Log likelihood, is it IID or some sequential constraints? Maybe this needs to be between 0 and 1 or something else. And then we can use some gradient descent or analytical solution or some derivative-free methods. So this is something like, you see, again, this is like very, very big or very general framework. And then by specifying these 4 steps, you end up with new model or maybe new algorithm and so on. In general, new approach. All right, so this was a recap so that we know what is the negative log likelihood function, what is the likelihood, what's the random variable, and so on. Of course, this is very brief because you are after machine learning course, after statistics, so statistical methods, so you should be more or less familiar with that, but just in case, where to look or what to look for and so on. So now we'll go to sampling methods, something like more, again, algorithmic, okay? And we'll start with a very simple example. So how to estimate a p-value, okay? So we more or less know that p-value is 3.14 something, but let's say that we don't know how to do that. But we know that the circle area is PR squared, where r is the radius, okay, of a circle. And we also know that if we want to calculate the area of a square, so this is just one side times the other side, right? And if we fit this circle in a square with a side of length 2r, so that is of 2r. So then we know that the area of this square is 2r squared. Okay. And we know actually that now when the circle is yellow and the square is purple, so we know that actually we know more or less how to calculate the ratio of these two areas, okay? And the ratio is nothing more than just p divided by 4. So in other words, p equals 4 times area of the circle and area of the square, all right? So what we can do, we can express it in the following way. So we can actually start sampling. We can start sampling from a square where side is 2r, right? And we can look whether a point hits the yellow part, so hits the circle, okay? So we know that it hits the circle if it is smaller or equal than the radius squared, okay? So this in the bracket, so this big I, it's in so-called the indicator function, and it is 0 if this x squared plus y squared is larger than r squared, and 1 if this is the case, this is true. Okay, so if the point hits the yellow circle. And now what is fascinating is that we can in fact start sampling from this square. We can sample a lot of points and we can simply average or see how many points hit the yellow circle, okay? And fascinating fact is that this will approximate our pi value, okay? And so we can approximate it by sampling, all right? So this is very, very interesting. And if we look at that, so this is a simple code written in Python that we sample 100 points, we check how many of them are inside, and we see on the left that this is estimate of pi, it's 3.08, not bad. But of course, we only sampled 100 points. If we sample 1000 points, we are getting a better estimate. It's getting 3.196, right? We are getting closer. If we sample another set of points, so 10,000 points, the estimate is 3.16. So we are getting closer and closer. So then in the end, ideally, right? If we are capable of calculating sampling these points forever, we should get to the real value, okay? And so this is the whole concept of sampling methods. So how we can maybe, instead of calculating something analytically, let's sample, let's generate some points, check their properties, and then estimate our quantity of interest, okay? So this is the idea of statistical thinking. And I would like you to think in this way, okay? Because very often mathematicians, especially, there are something like, we should calculate everything correctly and precisely and as closely as possible. But for computational, from computational perspective, it's actually the statistical way of thinking is very useful, because we can say, well, why we should bother, why we should calculate something, right, by hand. Let's do some calculations and then approximate this value, because in the end, in reality, we cannot never model some phenomenon so precisely that we'll get exact values, okay? We can anyway always approximate the reality. So maybe just approximating it by calculations, it's already good. And a little bit of history. So of course, sampling methods, they are called Monte Carlo methods, okay? And Stanisław Ulam, a Polish mathematician, during war, when he was a part of the Manhattan Project, so he was ill, and in his hospital he was super bored and he just played cards, right, solitary. And he was doing it again and again and again. And then at some point he thought, all right, so what is the probability of winning it, right? So for a very particular starting point, for particular layout with 52 cards, what is the probability to be successful in the end? Okay, so this is actually, the simple example shows again that this is extremely important to understand, okay? Because, for instance, if we will talk about reinforcement learning at some point, when we have a moving agent, a robot or whatever, so we know what is the initial condition, right? But the question could be, will this robot perform task in the end, right? We don't know these intermediate steps, but we can just ask this question. So the simplest way to do it is to just simulate it, okay? And Stanisław Ulam asked and thought actually about the same. We should, instead of incorporating extremely complex mathematical formulas, we should just simulate it and then average in the end. And the underlying idea is just approximate by sampling. So when we have some quantity of interest f of x, and if we sample this x's as much as possible, right, to infinity, we will in the end approximate the real quantity. Here's the integral, right? While in reality, calculating this integral could be extremely difficult, but approximating by sampling, averaging is very simple. And where do we use it? So in general, everywhere where we cannot calculate something analytically, so like normalization constants in statistics, statistical inference, we know that to calculate this integral is extremely difficult. So all expectations and so on. But also we use it in optimization, all right? And this one I would like you to pay a special focus on, special attention, because this will be the underlying principle for evolutionary algorithms, all right? So what is the problem with sampling, okay? So in previous slide, with this approximating pi, we're just sampling uniformly, right? We sample more and more and more and more and more and more and more points. But the problem is the curse of dimensionality, okay? If we do it uniformly, so really without blindly just sampling points, it turns out that we need a lot of points to properly approximate our quantity of interest, okay? So here in this slide, I'm saying actually that, all right, we need to be smart about sampling. We cannot do it, just naively and do it uniformly. We need to be smart. And why? Because if we take a unity interval with the same distance between adjacent points, for instance, 0.01. So between 0 and 1, we have 100 such points, all right? So let's say that we have 100 possibilities. So now if we want to sample all of them, it's easy, right? If we even want to repeat every single point 10 times and see how it behaves, we can do it, right? Or we can take just these 100 points, evaluate them and calculate average or whatever. However, if we go to 2D, 2 dimensions, so now we have a square, and this is a grid. And now how many points do we have? We have 10 to the power of 4, right? Because we have every single point in one interval, unit interval, we need to combine with every single point with the other unit interval, so we have 10,000 points, sorry. All right. So what if we go to 10 dimensions, right? Well, it's 10 to the power of 20. There are so many points. However, we have only 10 dimensions. So if we think of a simple image, and each image is represented by, let's say, 3 channels, RGB, and each channel is represented by 8 bits, so 2, 5, 6 possible values. And so now if we think of a standard image, 1000 pixels on 1000 pixels, so do your math. It's crazy number of possibilities. Okay, and now I was saying about 1 million pixels, 3 million values because 3 channels, and each pixel has 256. So each random variable, this 3 million random variables has 256 possible values. So it's really a lot. So so this 10 dimensions is basically nothing, right, compared to images. But even for these 10 dimensions, we see that the number of possible states is incredible. So if we want to do it naively and we just want to random them, we'll do it forever. We need some smarter techniques. So can we do better than just independent sampling? And here is the idea of this Monte Carlo methods and something which is called Markov chain Monte Carlo. So we will do in the following way. We'll have a one simple chain, and this chain means that we will make a new sample dependent on the past. Okay. So in other words, we need to have some kind of, it's called proposal distribution. So it samples a new point based on the previous guy, right? Previous point. And that's why we will have a distribution and a chain. And this chain of sampled points, ideally, it should cover the original distribution P of X. What does it mean? It means that it will sample points in regions where the probability mass is high, so events are more probable, more likely, and then it will not sample from regions where the probability is really low. A natural question is what kind of proposal distributions we can use, right? Because I will not delve into theory. It's a beautiful theory around it, but it's not the point. I want you to understand how to use these methods and also be aware of what kind of proposal distributions we can use intuitively. And we cannot use any proposal distribution. It must fulfill some conditions. So first, it's called irreducibility. So in other words, we need to ensure that if we start in some point, there is a positive. It could be extremely low, small value, but every other state is possible to achieve. Okay, so we are not excluding any point in the space. And second thing is that this chain cannot get trapped in cycles. So this is called aperiodicity. So there should be always a non-negative value probability of getting out from a cycle. Okay. Please remember these two remarks. In practice, of course, it limits our possible proposal distributions, but during this course, we'll use these very standard ones. Okay. And this leads us to a very nice algorithm called Metropolis Hastings. Okay, so what is the idea? The idea is that we start with some point, we pick it at random, and for some iterations, we do three basic steps. First, we sample our new point from this proposal distribution, right? We calculate, so we evaluate. We calculate what is the probability of this real probability P of X, what is the probability of this new point. We multiply it with this proposal distribution, the probability, but from going back to the previous step. And then we divide it by probability of last point times the proposal distribution. Okay. Then we sample some, and we call this acceptance distribution, probability. Okay. We have this minimum because the division, it could give us values larger than 1, and we just want to keep it as a probability. That's why we take minimum of 1 and something. Then we sample some value at uniform from uniform unit, and if this acceptance probability is larger than this u, then we accept this new point. Otherwise, we still use the old one, okay? And of course, we can always accept something, but then there could be some issues. I don't want to delve into that. Let's say that we just remember this algorithm is called Metropolis-Hastings algorithm. And for instance, the proposal distribution is just Gaussian with some specified variance, okay? And mean in current point. And P of x, we can know exactly what is this distribution, or at least we need to know what is the let's say unnormalized probability, how it's called. For instance, it could be x to the power of minus f, where f is so-called, for instance, energy or our objective function, okay? And maybe let's go into an example. So let's say that we have a function, a distribution. It goes like that. Oops, sorry. Okay, it has two modes. And now we will start. So we start in some point. We pick a new point. We calculate, so this is the Gaussian, right? We pick this point. Well, it has lower probability than this. All right, so it's not accepted. So we pick a new point here. We calculate the acceptance probability. It is here. Right, perfect. Now we again sample from some Gaussian. Let's say we are lucky. We go here. Again, this probability is larger, higher. Perfect. Let's pick a green one. Now we are here, and let's say that we pick here. Of course, in the meantime, there could be that we sampled something here, but it was not it was not picked. So in general, the chain goes like that, okay? Or maybe I can pick a different color. Let's say yellow. Right. So this is, oh, maybe yellow is not very unfortunate. Something, I don't know, steel, whatever. This is the chain, right? And these are parts that were not used as the chain. And now this chain can go here. And this chain will jump somewhere like that. And as you see, it starts covering the original distribution. But the problem is that it covers only one mode, okay? So how to deal with that? Yeah, let's see. So this is the Metropolis-Hastings, and we see already that it can cover nicely distribution after some time, of course. So it will just wander around so-called modes, so regions of high probability. But it can also have some issues, all right? And here is an example where these issues can come from. We see so on this, so we see this smooth is a distribution of let's say mixture of two Gaussians. And we have some variance equal 1, okay, on the left. And then this variance is just too small. If it gets to this one mode, it just only samples from this mode, okay? And it totally disregards the second mode. When the variance is too large, we jump a lot, and you see that this chain, it's actually like a lot of something like step functions. So it is stuck in some places. The acceptance probability is very low for so many points, that actually the number of accepted points is too small, all right? And just simply we covered two modes, but you see we wasted a lot of computations for disregarding many points. And then if we pick, for instance, variance 10, we have very good coverage. We covered two modes, and the MCMC approximation is very good, okay? And this Markov chain has a lot of accepted points. You know, like in life, nothing is for free. So in Metropolis-Hastings algorithm, the proposal distributions is crucial, right? And how we define it, it's extremely important. And again, not simple. Another example, a simplified version of the approach is just so-called independent sampler. So we just sample these new points from some distribution without having history, right? Not looking to the past. And again, it consists of 3 steps: generate, evaluate, and select. But of course, it could be way simpler in principle, but it can work worse. And then we have the last option, so-called Metropolis algorithm, when we change the proposal distributions to be symmetric, right? So going from one point to the other is as probable as going from one to the other. So let's say that we can take a distribution that is a circle or hypersphere, and this is uniform distribution, this hypersphere, okay? And then you just, whatever you sample there, it's equiprobable. And now I'm mentioning this cycle, we can call it neighborhood, right? And now you should see already a very close relation to these derivative-free methods, like this hill climbing, or iterative local search, and so on, right? So this is almost the same. The only difference is that now we have, everything is stochastic. So we are living in a stochastic world. So this behavior of this algorithm is randomized in a sense, okay? But the cool thing is that we have convergence properties. So for this algorithm, we if everything is defined properly, we know that in the end, somewhere we'll get to the good point. All right. The next algorithm is called simulated annealing, and the idea is like Metropolis-Hastings, but we introduce another quantity called temperature. So the idea is that when we have this, let's say these two modes in Gaussian, we can actually miss this mode because we started in the, let's say, wrong place. But if we now flatten this mixture of Gaussians, so then there is a higher probability that we will jump between two modes, okay, if this is flattened. So this is the idea of simulated annealing. This is also the name coming from the idea that it's something like in the beginning you have, like everything is probable as the temperature is high, so they can jump between modes, and otherwise when temperature is high, the particles are getting less willing, let's say, to jump around, okay? And the extra step is that we set this temperature, so-called cooling schedule to so that it goes lower and lower, okay? And the cool part is that if we have this unnormalized probability expressed as follows, that we have exponent of minus objective function, for instance, so then this p to the power of 1 divided by t, so this 1 divided by t just goes to the exponent, okay? And this is something which is called the Boltzmann distribution and Boltzmann formula, okay? You will see in many books. And the cooling scheme, one example is that we can take something like that the 1 divided by t just goes up, so the temperature goes down, right? And so these are very algorithmic algorithms, so they're very algorithmic perspective. What is interesting is that we can do optimization through sampling, okay? So far, I presented a couple of algorithms, sampling algorithms. You can use them for sampling, but interestingly, we can use it also for optimization, okay? So there is a and again, we can say that this is like randomized optimization, okay? So let's say that we are interested in minimizing function f, our objective. But in fact, we can consider a distribution of this form, so Boltzmann distribution, that we have this negative objective divided by temperature. And by changing temperature, we can consider almost uniform distribution if temperature is really high, because then, you know, we flatten it. Or it could be very picky, so it's something like directing only once when the temperature is low, okay? And so then for almost uniform distribution, so very, very high temperature, we have very good exploration because points can wander around. But for very peaky distribution, we have exploitation because then we are going around the peak. And here is an example. So on this left upper corner, we have very high temperature. So we sample a lot from this from the space, and then we see that we have a lot of accepted points. Then when we go to the right top corner, so we getting a lower temperature, and so it's something like getting it has a better maybe coverage that we also take into account the probability of this modes, right? Then bottom left, the temperature is getting lower, and then on the right, bottom right, we have very low temperature, so it gets peaky around one mode. And what does it mean? It means that actually now, if we start with some optimization problem, so then first we start to cover the space. We look for the modes, in other words. And then once we make this temperature higher, our algorithm will start picking, it should start picking the mode that it is more peaky and peaky, okay? So higher values of, or lower values of the objective function, okay? And that's for today from this lecture. So please remember that there are two things very important. First thing is that sampling methods should be smart in some sense because of the curse of dimensionality. Second is that we can use randomized algorithm to also optimize our objective function, all right? And so a lot of algorithms that we know, in fact, from these derivative-free methods, they could be derived from Monte Carlo, Markov chain Monte Carlo methods, all right? So, and the idea is that we will just change, you know, generate step to something, we'll set, then the acceptance probability will be, for instance, deterministic, so no stochasticity here. And then we end up with, for instance, iterative local search, all right? Also, when we will talk about evolutionary algorithms, again, this will give us, this will also give us a very good perspective because, in fact, evolutionary algorithms are like this, you know, multiple chains going together, and the proposal distribution will be defined by this mutation crossover, okay? So please keep it in mind. I hope that this lecture wasn't too heavy for you. If it is, so then we can discuss it, of course, on our Q&A session. Thanks a lot.